It's too small. 28 are there. No, 28.
Yeah, we are late. Please start.
Good evening to you all. On behalf of Center for Excellence in Research and Development of Nanoelectronics Theranostics Devices, under the aegis of Center for Nanotechnology, Indian Institute of Technology, Guwahati, I welcome you all to the 6th National Workshop on NEMS, MEMS, and Theranostic devices. The theme of the 6th edition of the workshop is Nanoelectronics and Theranostics in post-COVID-19 pandemic. To start with, we have welcome address by Professor Arun Chattopadhyay. His research area is mainly focused on broad areas of nanoscale science and technology involving synthesis, reaction, and organization of nanoscale materials and their application in problems related to chemistry and biology, particularly working with composite materials, chemical locomotion, and in nanobiotechnology. Professor Arun Chattopadhyay has been selected for J.C. Bose Fellowship in this year, 2020. He is a Fellow of Indian Academy of Sciences, Royal Society of Chemistry. He has received many awards. To name a few, Young Career Award in Nanoscience and Technology, and also Swarna Jayanti Fellowship from the Department of Science and Technology, Government of India. He has more than 165 papers and many patents. Now I'd like to request Professor Arun Chattopadhyay to please come over and deliver his welcome address. Sir, please.
Yes, thank you very much, Paromita, right?
Yes, sir.
And now you see, I talked to my colleagues that earlier we used to see first mobile phone as an introduction to regular habits. Now it has become from 2020 mobile phone plus masks. So 2 M's are there. So maybe we don't want more or no, I don't know. But we go to nano now, N. So why is it that we still need nano? Why is it important? Nano is approximately 40 years old. It's not 50 yet. It started in 1981. A little before that, in chemistry, in physics, it was there, but with the invention of atomic force microscopy and scanning tunneling microscopy, starting with 81, the official announcement of nano actually became clearer to everybody. Why is nano important for all? Now, if you notice here, mathematics is 2000 years old, 2000 plus years old. That is common to all. Everybody needs to learn mathematics. Then came physics, approximately 450 years old. Then came chemistry, that is approximately 200 years old. Then came biology, that is 100 years old, 100 plus. If you say Gregor Johann Mendel, then it is a little longer, but approximately 100 plus years old. The nano, what is nano? Let me explain to you what is nano and why everybody needs it. From the beginning, human being wanted to have control over properties of matter. But many people tried but failed, including Newton tried alchemy to transform matter from one to another. Now, mathematicians gave in numerical values for properties of matter and prediction. Physicists discovered the properties of matter, and it became in the hands of chemists to transform the properties of matter. How? If you have chemicals transforming atoms. I'll give you an example. All of us drink water, H2O, that is H2O. If you add one carbon to hydrogen, it becomes CH3OH. If you drink that, you will first become blind, then one will die. So CH3OH is not good. So chemists said you add one more carbon, two more hydrogen, that becomes C2H5OH. That became a big business to the world, especially for all governments, including prohibitions. So that you transform matter and their properties by changing atoms and something called chemical bonds. Now that was exclusively to the chemists. Then it became biologists who were interested also in transforming matter through using biological system, living systems. And now engineers want to change properties of matter, physicists want to change properties of matter beyond subatomic particles. So how do you change? Now scientists discovered that if you change dimensions of matter at the nanoscale, you can change the properties of matter. In the periodic table, all properties of matter are decided by nature. That is called atomic properties. If you have silver, if you have gold bulk, these properties are called bulk properties, you cannot change. But when you go at the nanoscale dimensions, means 10 to the minus 9 meters, say 1 to 100 or 1 to 10 nanometer, you can change the properties of matter by changing the dimensions. And this change in dimensions can be handled by chemists, physicists, engineers, biologists, everybody can do it. So everybody can contribute, participate, and benefit nano. It became apparent after that if you use nanoscale materials, you can have larger matter constituted of nanoscale materials with properties that you can control. Just like you have atoms to molecules, you can control the properties of molecules by changing the constituent atoms. Similarly, by changing the constituent nano, you can change properties of larger dimensions, matter of larger dimensions. Now, how do you conceptualize nano? Now, all of us go to barber or salon to cut our hair. Now that you use a scissor. Now cut your hair in a perpendicular direction 1000 times. You will get 50 or 100 nanometers. That's very difficult. Only physicists can do it. So that once you do it, that your hair will become nanoscale material and it will have a different property than what you see. So you can have properties of matter, tune and take advantage. What is the advantage? You can have high or low boiling point. You can have electrical conductivity. You can have not electrical conductivity, semiconductivity. So all those properties of matter one can tune at that level, and that is now accessible to all sections of scientists and engineers, chemists, physicists, biologists, mathematicians, engineers of all kinds. So that becomes very important for all of us. Now you will ask the question, so it is almost 40 plus years old, what is left for us? The realization of nano is not yet done fully. How? If you can use nano robots for surgery or for pursuing matter inside the biological body. Imagine a robot inside your body and giving you information. That has not been realized. So that, if you can be realized, it's a big advantage. That's for youngsters to realize and give it to the society. So we invite all of you to learn and contribute to the nanoscale science and technology so that all sections of the society can benefit. And now we are at the best time to live, because science can be pursued by anybody now. Engineering can be pursued by anybody now from anywhere in the world. That was not the case 100, 200 years ago. Once that is settled now, let us all join to contribute to the science of nano at the small scale and bring the fruit to everybody else. I thank you very much for participating, and I hope you will enjoy and benefit from this conference. And we are all benefited from the leadership of our director, Professor Sitaram, and I hope he will be bringing to us the great inspirations he always carries for all of us. And his lecture is next, which will be announced by my colleagues. Thank you very much. Next.
Thank you, sir, for your informative and motivative talk.
The meaning of 1 milliseconds.
So shall I go ahead? Thank you. So very good afternoon to all of you. I'm very glad to be here to inaugurate the 6th National Workshop on NEMS / MEMS and Theranostic devices, NWNTD 2020. Distinguished colleagues, students, and also the participants of this national workshop, I'm very happy to inaugurate this workshop. First of all, a warm welcome to all of you to this online workshop, and I'm very sure this workshop will disseminate a lot of industry-based knowledge in the nanosciences or nanoelectronics. This Center for Excellence in Nanoelectronics, covering devices and materials of size 1 nanometer to 100 nanometer, and the theranostic devices, which are non-invasive or minimally invasive devices. It's a very key aspect in today's healthcare technologies. To deliver healthcare technologies, this is going to be not only healthcare, I think any technologies, this is a fantastic tool. And I'm very happy that IIT Guwahati has a fantastic group working on these areas. So this project is actually, I understand, that's sponsored by MIT, Ministry of Electronics and Information Technology. And you're holding this workshop between 1st to 3rd December to improve the academic awareness on the micro or nanoelectronic fabrication, characterization, and also the new developments in this area. And also you're trying to focus particularly in the northeastern region of the country, which is, I think, it's a very important development. This vision to link up the high technology to the northeastern region of the country to bring changes is very critical. The contribution from the mainstream interdisciplinary team at IIT Guwahati in this area is very significant. So this kind of activity will create a high quality manpower development, cutting edge technologies for diagnosing severe diseases, or many other aspects which will be tackled by this group of people. This center has done tremendously well in the last decade with a lot of transfer of technologies and commercialization of R&D efforts. For India to becomes an Atmanirbhar Bharat, this kind of attempts are very, very critical. So you need to translate the research and developmental activities into products and processes which are useful to the society, which are much affordable and also has a huge cost advantage to the significant masses. Unless we leverage this advantage in the areas of healthcare, we will not be able to solve the healthcare problems of the nation. The social and cultural issues can also be better taken care when R&D activities are done with a focus on applications and particularly solving the real life problems of the society. So I hope that this workshop will disseminate information to the young people and motivate them and also expose them to the real life problems faced by the society and challenge them to solve these problems effectively. The post-COVID pandemic, our dream at IIT Guwahati is to create a unique opportunity for our young people to create new innovations. And in this particularly, I would like to highlight where we can reach in the healthcare sector, the medical device, biomedical device innovations. So, and also we would like to, I would like to tell you, our dream is to also start a program on developing this biomedical device innovations. Maybe you can call, some of you might have seen bio design program of Stanford. On a similar lines, if all of you can think about with a passion for entrepreneurship and commitment, I think we can make this happen very effectively. Innovations leading to lower cost of testing, care, and also minimally invasive procedures and shorter recovery times are very critical in this area. So through technology innovation, I am very sure, if not putting a robot into your body, some of these definitely can be done. Maybe a robot, as Professor Chattopadhyay said, robots might take much more time to get into your body, but definitely some of the things like lowering the cost of the testing and minimally invasive procedures and also shorter recovery times of the people who are using this kind of a technology for care is definitely possible, and the world has already shown, and I think our colleagues are also no way behind this. They are very in advanced stage. So I hope that this group, which is a very multidisciplinary, having biologists, chemists, and then physicists, and then engineers, both chemical, mechanical, electrical, including civil engineering, which is a multidisciplinary kind of an attitude which can come, which can bring in a new rigor and force to start a program on biomedical device innovations, tying up with medical doctors, is a very key issue. Our vision to be a leader in this Northeast in advancing this healthcare technology in the nook and corner of the Northeast states through entrepreneurship and their startup, who will be trained by our team of the nanoscience group at IIT Guwahati. I'm very sure this is very possible, and I'm not seeing too long to, our colleagues will not take too much time. I know that they will deliver this dream of IIT Guwahati to become the leader in this area, not only in the Northeast, for the entire country. I'm very sure nanoscience program, as Professor Chattopadhyay was saying, is not even 50 years old, but India is actually a leader in this area, and among them, IIT Guwahati is not behind. So we are very happy about this progress, what our colleagues have done, and I hope that they will have much more success in this area. And I'm happy to inaugurate this workshop today, that is nano and microelectronic mechanical systems and theranostic devices 2020 in an online mode. I congratulate all the colleagues of this center who are actually from a different departments, multidisciplinary activity, which is also the dream of our National Education Policy 2020. So I wish a great success to this team. And I also wish that this workshop will be creates a learning environment for all youngsters who are not only PhD students at IIT Guwahati and many other students who are attending this workshop all across India, and all the other people who are part of this today's workshop deliberation and our inauguration. I wish them a great success. With these few remarks, I again thank all the organizers to inviting me to say a few words and motivate you. I thank for this opportunity once again and wish you all the best. And I inaugurate this workshop very happily. Good luck. Thank you very much.
Thank you, sir, for your valuable and inspirational talk. Now I'd like to request you to please inaugurate NWNTT booklet. So please.
should always make in such a way there is only one step.
All the best.
This is too traditional. Chalo. Done. Everybody is in.
Thank you, sir.
Director's lecture is over or there? He's done. Only yours now. See, Pankaj, come here. No. No. That chair is regular chair.
Moving on, we now have speech by our head of the center, Professor Dipankar Bandyopadhyay. He is a professor in the Department of Chemical Engineering. Sorry for the delay because of some network issue. Our head of the center, Professor Dipankar Bandyopadhyay. He is a professor in the Department of Chemical Engineering and Center for Nanotechnology, IIT Guwahati. His research area is mainly focused on sensors, materials for advanced research and renewable energy and technology, MEMS Theranostics, artificial microboards, and so on. He is a nominated member of RSC, ACS, IICHE. He has received many awards. To name a few, Gandhian Young Technology Innovation by Rex Christie Appreciation Award and also Gandhian Young Technology Innovation Award. He has been a visiting faculty under the COSSC program KTH Stockholm, Sweden, also at the Yungnam University under the WCU Nano Center program, South Korea. He has more than 130 papers and 28 patents. So now I'd like to request Professor Dipankar Bandyopadhyay to please address the gathering. Sir.
Thanks, Paramita. So hi to all. A very good afternoon. I welcome all the participants across the globe in this workshop. This is our yearly pilgrimage. Generally, we are able to really maintain this for the 6th time. Okay, and we are very happy that this time is led by Uttam and Biman, and they have organized a very nice recipe. I should say that it's a combination of very good lectures with a lot of training sessions. Ideally, the plan was to have these hands-on training sessions, but unfortunately, due to this pandemic situation, we have to go online. Nevertheless, I hope that all of you will enjoy the training sessions because I have seen the cuts. You know, people have put, the entire Center for Nanotechnology has put a lot of effort in composing those lab sessions and at the same time, all the other requirements. So first, on behalf of the entire team here, I welcome all of you in this particular workshop. And then I wish that you have a good time next 2 days exploring all the nitty-gritty details of science as well as technology. Just to put one small emphasis here that we try to keep the workshop focus both on science and technology. So you will find a lot of lectures which will be having high-end science, and at the same time we also don't miss out the translations that are happening around this science. So you will find a lot of industry participant speakers who are going to talk about different types of technological aspects that are associated with nanoscience. So we encompass both nanoscience and at the same time nanotechnology in order to really explore all the possibilities associated with what we have learned up to this point in terms of science, and then how we can use it for the betterment of the society. Okay. So with this, I think, I welcome all of you and I wish that all of you have very good time. I just wish to thank our director, Professor T.G. Sitaram, for making this time for the Center for Nanotechnology and all the help that we received from the administration. And last but not the least, our funding agency, NITI, who have been very generously supporting us in developing all the facilities, in implementing and installing all the facilities, and then helping us in exploring all the state of art or cutting edge research associated with nanoscience and nanotechnology. I welcome all of you on behalf of the Center for Nanotechnology. Thank you very much.
Thank you, sir, for your speech. Now I'd like to request Debashri to please take over from here.
Thank you, Parmita.
Good morning. So, 2 chairs sideways.
Now moving on with the program, I would like to invite Professor Biman Mandal, who is the convener of NWNTD 2020, to take over and address the participants. Professor Biman Mandal is working as a professor in the Department of Bioscience and Bioengineering and Center for Nanotechnology in IIT Guwahati. He is a renowned researcher working in the field of biomaterials and tissue engineering, 3D bioprinting, and human tissues and organs. Professor Mandal has more than 140 publications and 17 patents. He has bagged prestigious Young Scientist Awards from the Indian National Academy of Sciences and National Academy of Sciences, India. He has won Nasi Scopus Young Scientist Award for high citations and B.M. Birla Science Prize in Biology, along with many other awards. Recently, he has been awarded the prestigious Swarna Jayanti Fellowship by Department of Science and Technology in Life Science for the year 2019 to 20. Sir, please take over and address the participants.
A very good evening to everyone. As convener and on behalf of IIT Guwahati, I would like to take this opportunity to welcome all the participants, delegates who are part of this 6th NWNTD workshop. And we all hope that it will be an enriching experience for all of us. We would have loved to have you, physically here and host you with the beauty of this campus and the learning experience that we could have offered to you. Unfortunately, COVID-19 has been playing spoil sport the entire year. But on a positive note, still, we would like to go ahead and we have planned a very exciting and stimulating 3 days for you, both comprising of lectures by eminent speakers across the globe, and also hands-on experience on cutting-edge technologies that we have lined up. And we feel that this would be very, very useful for you all to learn about cutting-edge science that is ongoing currently. And as convener, we have of course tried our best to give you and arrange all whatever is required, but you feel free to reach to us if any difficulty you face across these 3 days and beyond. We'll circulate the copy of the abstract book already in terms of PDF to you so that you can go through. However, we welcome and we sincerely expect a lot of interactions from the participants after the talks and the lab sessions that happen, because that is the most fun part, where you would really love, have interactions with the eminent speakers and learn a lot. And before I end, I would like to thank our director, honorable director, who have inaugurated, Professor Arun Chattopadhyay and Professor Dipankar Bandyopadhyay, who are principal investigators for this current project. and who's under this sixth workshop of NWNTD 2020 is being organized, and me and Uttam are doing it for the first time, and we are new entrants to the Nano Center as well. So this is the handholding we are getting, and we are pretty excited about what we are learning. So we expect you to learn and learn along with us. And with that, I would like to thank the entire team of organizing team who had been putting a lot of effort last 1+ months. Though it is a 3-day event, but a lot of activity has happened behind the scenes, and they really deserve all the good wishes in terms of putting it together. So I would like to thank everybody who has been putting their efforts to put up the show, and we look forward to all your participation. Best regards and stay safe.
Thank you so much, sir, for sharing your experiences. Now we will move on.
Actually, we are going before time.
It's okay.
Speaker is not joining.
We'll wait. We'll have questions now. No, Uttam.
Uttam will take over and speak for them. He can talk about hydrogen.
Now I would like to invite Dr. Uttam Manna, who is the convener of NWNTD 2020, to take over and address the participants. Dr. Uttam Manna works as an associate professor in the Department of Chemistry, IIT Guwahati. His research interest is focused on anti-wetting properties of materials and superhydrophobicity. He has more than 70 papers and multiple patents. He has bagged awards like Humboldt Research Fellowship for experienced researchers, and he is also a fellow of Royal Society of Chemistry. Sir, kindly take over.
Thank you, Devasri. And as my the other colleague, Professor Biman Mandal, is a co-convener of another convener of this NWNTT 2020. So this is the 6th version. So this particular conference introduced in 2015, and in 2019, if I correctly remember, 2019, I was invited in this particular conference as an invited speaker. And when I came here, and then I found like it's an amazing platform. Generally in the conference, we know there are different talks from academic experts mostly. But here in this particular platform, it provides proper avenue to initiate or accelerate collaboration between industry and academia. And it's a good mixture of talks from both academia and industry, which is not only the key attraction. Another important thing is like hands-on demonstration of state-of-art infrastructure. Many times we know good work, the product and all, right? But we don't know, suppose when you go in a restaurant, you know about the food, which is very good, biryani and other things, right? But you don't know the kitchen, and you don't know how things cooked, right? And how important to have a great kitchen to cook food. Similarly, to get a state-of-art research, the facility is very important. And hands-on demonstration on those infrastructure. And in that sense, the Center for Nanotechnology in IIT Guwahati doing a great job. I was really surprised and mesmerized by seeing all of this. Top of that, there have panel discussions. There have experts from industry who can give their opinion, comments about how to formulate a patent, how to do this technology transfer. And also, it's a kind of amazing platform where you come to know that how to translate your research from the laboratory to technology transfer to a product which can be commercialized. which is, always we dream for it, but, this is a place where basically we can see how things goes from laboratory to, actual product which can be commercialized. So I was really happy and honored to host this kind of, to take part and, organizing, involved in the organizing team to conduct these things. And top of that, I should start with, thanking the great organizing team, which is the long list, but I should definitely take a few names. Dr. Pranjali Das, Anand Sarup, and Sandan Sarma. So they constantly helping, and all these participants timely they got informed about all these details, the schedules and all. And this is also very much new for us to organize such a things in online platform. We know how to do things, in offline, where physically people are there. So the struggles are different in different modes. But yes, we try to do it such a way that people can really enjoy this platform and they don't feel like this is something less than that offline regular mode. Now, just to brief you about this particular conference, so there will be total 5 sessions. So in day 1, only inaugural sessions where there will be 2 talk next is coming, one from Reliance Industry India and another one is from Samsung India, and they will deliver their talk related to technologies what they are adopting in their industry. And then in next 2 days, in day 2 and day 3, there are 2 sessions, forenoon and afternoon sessions. Mostly in forenoon session, there are lab demonstration, and then there are talk from academic, the expert from academia. And in afternoon session, there are mostly the 4 talk, and both are from the talks are from both academia and industry. And there will be a panel discussions, which will share some of the success story about the technology transfer from the research, what I just discussed briefly, so that, how to transfer, how to, mold your research to, commercialize product. So those success story will be discussed in those panel discussions. Also very recently, in this very difficult and different situation like COVID-19, some of our senior colleagues, they basically came up with some idea, and then they have implemented those ideas, and they in fact materialized those concepts. They're very much fruitful to fight against COVID-19. That success story, that struggle, how to start with the scratch and then transferring something to which is very fruitful for the nation. That success story also we share with you all. And I thank our director, from his busy schedule, he find out some time for us and giving the motivational and encouraging speech on this conference. With that, I'll conclude here, and I hope you all will enjoy this whole session. Yeah, and then you all join us in 5:30. So there will be 2 talks from industry. As I said, one from Samsung, another will be from Reliance. 5:30. 5:30. Yeah. Thank you so much.
We join faster.
Welcome back, participants. We will now resume with the sessions, and we will start the talk and presentation sessions right now. So I would like to tell all the participants that those who have joined us through the Microsoft Teams as well as through the YouTube live streaming, they can post their queries and questions in the chat box section, and after the talk we can take up their questions, and there will be a short Q&A section. So there the queries and questions can be discussed. So now I would like to invite our first speaker, Dr. Kaushik Saha, to take over and present his talk. Dr. Kaushik Saha obtained his graduation and doctoral degrees from IIT Delhi. Thereafter, he joined STM Microelectronic Limited in 1996. He worked as principal member technical staff in the Advanced System Technologies Group till 2013. Thereafter, he joined Samsung Electronics in 2013. At present, he is CTO, Samsung R&D Institute, India, Delhi. His research interests are in the areas of advanced processor architectures, parallel algorithms, and low power SoC design, especially for IoT devices and services. He holds an adjunct faculty position in IIT Delhi. He is deeply involved in standardization and is a knowledge partner for NASCOM. He serves as technical advisor on the program steering groups for the National Microprocessor Development Program and the NAVIC Receiver Development Program, and as a member of the National Working Group on Microelectronics constituted by MeitY Government of India. Sir, please take over and present your presentation.
Hello, madam. Hello.
Yes,
Are you
sir.
able to? Actually, I am connected on mobile due to some problems. You are Dr. Pranjali Das, right? Hello. Hello.
Sir, I'm Devashri. I'm a student here.
Yes, sir. Sir, please.
Actually, I have mailed you the presentation. Can you please bring it up on the screen and scroll it for me? Because I am not able to do it from the mobile.
Yeah. Okay, sir. We'll do it.
I have sent it to Dr. Das and Dr. Manna. You will have received it from my Hotmail account. Hello, Devashri, please don't make me presenter. Hello.
Yes, sir. We are just opening it.
Just a okay, fine. So take the presenter rights from me, please.
So is it visible to you?
Sir, the screen is visible to you?
Hello, can you hear me?
Yes, sir, we can hear you.
Okay, so please scroll to the next slide. Okay, good evening all. I am sorry for the late start. So this lecture is going to be about swarm intelligence. Actually, all of you are aware of machine learning and machine intelligence, artificial intelligence, etc. Am I audible?
Yes, sir.
Okay, so in machine intelligence and machine learning, artificial intelligence, we typically try to mimic the behavior of human beings. So we try to mimic human intelligence. So we try to get from our machines, we try to get the kind of behavior, decisionary behavior or classification behavior, which we typically observe in human beings. But apart from this, there's another big world in the animal world, a big world of intelligence in which there is swarm behavior among very small animals like insects and birds. You can very well visualize that small insects like say bees or ants or small birds like say, sparrows, etc., are small animals. So obviously their nerve is small and they're naturally, because of the simplistic nervous system, they have very limited decisionary powers and classification powers, right? But yet somehow they are able, when they collectively work as a hive of bees or a hill of ants, an ant hill, or a flock of birds, they're able to actually execute some very complicated tasks in a collective manner. So a single bee, an individual bee may not be able to do very much by way of complex tasks, but a bee swarm may actually build a very complicated structure like a hive, for example, right? You know, a beehive is a very complicated, complex geometrical structure. Similarly, an ant hill would shows some very organized behavior in terms of complexity of tasks, which would be very difficult for us to imagine how a single ant would go about doing it, right? Obviously, then there is some kind of collective intelligence that is at work, which is not within the powers of a single animal, of an individual animal. So this is collective behavior that we're talking about. These are decentralized, self-organized systems. So in a bee swarm or an ant hill, there is really no central intelligent controller. For example, it is often very a common mistake is to think that the queen bee or the queen ant is the controller of the swarm of bees or the ant hill. But this is not the case. The queen is actually just a machine or an animal which is responsible for reproduction in the ant hill or the beehive. But to do the complex tasks, etc., the queen has really no role. So somehow, by some mysterious association between the bees, there is a they are able to associate with each other, and in a decentralized manner, organizing behavior emerges, which is able to do a complicated task. So we can see that these are systems which are comprised of populations of agents with simple rules. So obviously the rules have to be simple because the animals are simple. They have simple nervous systems and simple muscular systems. The one thing that the one factor that works in their favor is that they're able to interact locally with each other. which means there is communication between neighboring animals, neighboring bees or neighboring birds or whatever. They interact with the environment to get their information, the stimuli from the environment. And then this interaction with the environment and the local interaction is able to generate some intelligent behavior, right? Some collectively intelligent behavior. Is this understood? Right. So here you can see an anthill or a beehive or a flock of birds. So as can we evolve? Can we study this? The question is, can we study this behavior and then see if this can be applied to, say, a swarm of robots, mobile robots, for example, robots which are not fixed to one point in the assembly line of a product, but robots which are able to move. All right. So identical robots can communicate with each other and somehow carry out a complex task by by sending information to each other and taking stimuli from the or taking sensory inputs from the environment. So this, if we can mathematically model this, then this could lead to an intelligent, emergent global behavior working towards solving a global large-scale problem. Like, for example, movement of complicated materials, complicated material movements in a warehouse, or doing a complicated assembly job, which can be done by a swarm of robots or drones. Any questions on this slide? All right, let's go to the next slide. Am I audible? Hello?
Sir.
Okay, please scroll to the next slide. So what are the capabilities and benefits that we look for in a swarm with intelligence? So what are the capabilities and benefits of swarm intelligence? So capabilities are that clusters are formed between similar, typically similar, but also maybe dissimilar collection of agents. So similar collection of agents clustering together would be, for example, a flock of birds or a swarm of bees. They are able to optimize their tasks very efficiently, which means they can find best or minimum cost solution from a set of from all the feasible solutions. Let us say, for example, the swarm of bees is looking for food, the nearest, the shortest path to a source of food, right? So this could be a typical example of looking for a minimum cost solution in from among all the feasible solutions, right? So furthermore, this optimization goal can be applied, for example, in routing. As I said, the finding the shortest route to a source of food. So can we apply this for routing tasks, for example, in robotics? Can we apply the same idea? And again, it's a combinatorial problem that can we actually can we actually have them optimization tasks like scheduling and load balance, right? So scheduling in jobs in a computer cluster, in a cluster of servers, let us say, right? So in a cluster of servers which is trying to schedule a queue of jobs, relative position of the job can be determined. It's a combinatorial problem already, so that the overall throughput of the entire cluster of servers is maximized. Benefits is there's a great deal of flexibility. The swarm or the colony can respond very fast to a disturbance or external changes, because disturbances can be locally sensed by the agents which are closest to the disturbance, and they can respond as fast. They can respond very fast within a very short time. This is robust because loss of a few agents can be recovered by simply other agents coming in to take their place. This is scalable. A swarm can be small, but the same algorithms and the same intelligence can be expanded to a larger swarm. Decentralized, so failure of a central agent does not lead to a catastrophic failure of the system, and self-organized. So the colony or the swarm is able to find is able to organize itself by following the simple rules to find the optimum. Therefore, the sum of all these benefits results in adaptability of this swarm to changing conditions and arriving at optimum solutions even with fast changing conditions in a very short time. Any questions on this particular slide? Hello. Okay, next slide, please. Thank you. So this is one of the simplest, one of the primary types of algorithms or optimization methods that are used in swarm intelligence. This is called ant colony optimization. All right. So please look at the figure on the top left. So there's a hill of ants, a nest of ants, and there's a source of food. So obviously the ants have been going to the source of food by the shortest route. Now the conditions change and an obstacle is introduced between the source of food and the nest. So now obviously the challenge faced by the ants is to find the shortest route past the obstacle to the source of food. Right. So you can see here that there are two paths. The path on the left is longer than the path on the right. Now the challenge before the ants is to find the path on the right and concentrate all their efforts over there. So what are the algorithm steps? We represent the solution space by a graph. Now the graph has a nest on the left and the source of food on the right. There is an infinite number of paths really. In this case, multiple paths are shown. We set, now what we have to understand in this case is that whenever an ant passes along a path, it deposits a perfumed substance, an essential oil, which sends out a scent for the following ants, and this scent is called a pheromone. Right. So whenever an ant walks on a particular path, it keeps depositing pheromones on that path, and as the ant walks, the amount as various one ant after the other walks on that path, an increasing amount of pheromone builds up on that particular path. Right. Now let's use just our common sense. The shorter path will take less time to traverse. So let's say many ants go out on the various paths. The shorter path will naturally get a greater deposit of pheromone within the same amount of time. So the longer path, let's say within 5 minutes, the shorter path, assuming that the same number of ants go along all paths, then the shorter path will, in 5 minutes, will get a greater concentration of pheromones. This will lead to more ants in the next 5 minutes, say 5 to 10 minutes, to take the shorter path because they will follow the path with the stronger pheromone concentration. So over a period of time, maybe 15-20 minutes, the amount of pheromone will keep building up on the shorter path, and the amount of pheromone on the longer path will be less. Now we also introduce an evaporation factor. So if a path is not visited and the pheromone is not deposited on that, then the pheromone actually evaporates from that, right? So now you can see the update formula. Whenever an ant walks on a particular path, the probability of choosing that path increases by a factor beta, right, which is the pheromone deposition rate, and it increases by the factor beta, which is given by the deposition rate. And if the path is not visited, then the pheromone evaporates by a factor alpha, right? Now the pheromone deposition it depends on beta, the path length itself, to reflect the fact that the longer path will get less pheromone over a period of time. So it's inversely proportional to the path length Li, and it is directly proportional to the amount of pheromone that is there already, that is pi. All right. So using this update formula, what happens over a period of time is one of the paths keeps getting reinforced in terms of pheromone, and therefore the probability of taking that path increases. On the other paths, the pheromone keeps evaporating, and the amount of pheromone deposited on it reduces. All right. So after a few iterations, all the ants will take that particular path, the shorter particular path. Now, obviously, from the dynamics point of view, this is a recursive equation, the recursive update formula. So it will the stability of the algorithm depends greatly on the factors alpha and beta, which must be chosen with a great deal of care. So this is the one of the algorithms that is used for mimicking swarm intelligence. This is called the ant colony optimization. Any questions?
No, sir.
All right. Is this known to the audience? Anyone? All right. Let's go to let's go to the next slide then. Please scroll to the next slide. All right. So what we have done in our work is that we have tried to use this ant colony optimization for attack detection in in a cluster of smart meters. So you are aware of smart meters, which are used for metering electricity, electrical consumption, right? Consumption of electricity. So the primary goal of our work is to detect various kinds of attacks in IoT environments. So, you know, IoT today is evolving towards clusters of tens and hundreds and maybe even thousands of devices in proximity to each other, and all of them talking to the others to achieve a certain objective. Let's say monitoring of the indoor monitoring of the environment in a building, and then doing climate control. Okay, so here we are considering a cluster of electricity meters, and the point is electricity meters can be tampered with in various ways to not only just reduce the electricity bill, but they can also be tampered with the intention of actually putting a building or a neighborhood into a dangerous position with if somebody has a malified intention, right? So by attacking the meter, the smart meters, which contain software, what people can do is they can actually stop the electricity supply to a certain neighborhood or a certain area, right? So the idea is to treat this collection of meters in electricity meters in a neighborhood like an IoT cluster, and to detect any attacks on any meter by any persons with malified intentions. So the left-hand picture shows that the kind of tampering that can be done on the various kinds of tamper that can be done on metering. So, for example, you can bypass them, right, and take electricity without it being registered in the meter. You can get it disconnected, right, and then draw electricity directly from the main bus. You can actually make the meter run backwards, therefore subtracting readings, right? And then you can by man-in-the-middle attacks, etc., you can actually recover or steal passwords from the meter to make it do unwanted things, right? So these are various attacks that are possible. In all cases, this will be treated as an anomaly, right? And the idea is to detect the anomaly as an attack in the metering environment and take corrective action as soon as possible in real time, without having to take a recourse to the back end, because that may take a long time. So what happens is that, please look at the picture on the right. So these are multiple meters, maybe installed in multiple houses, finally going to the substation. So the thick curved line is the electrical bus, which is going from the substation to the various meters, to the various houses, let's say. These meters also connected to each other by Wi-Fi or some kind of wireless mechanism to enable metering. So the electrical energy or the electrical power comes on the thick curved line, the power bus. The communication is through Wi-Fi between meters and from meter to substation for getting the readings from the meter. So you may have seen this kind of smart meter nowadays, in which do not require a meter reader to come along to the house and take a physical reading. It can be done remotely by means of Bluetooth or Wi-Fi. Right? Now the point is, each node or each meter has a certain pattern of electricity consumption depending on the domestic usage. All right. So once there is some kind of tampering, the distribution or the histogram of these readings will change. So as a result, there will be a change in the entropy of the time series, which comprises, which reflects the readings on the meter. The idea is to detect this change in the entropy and then take action by and take action, some corrective or preventive action. Now the problem is the meter which is affected, that itself cannot detect this, because that may be that may no longer be in a position to execute any of its own software, right? So it may have crashed, right? Its processor may have crashed. So the idea is that the neighboring nodes, they should be able to detect this condition and then create an alarm or create a corrective action. So this is pretty much similar to, let's say, a flock of birds which is attacked by a predator. So the birds that are directly attacked will be observed by their neighbors, right, who have not been attacked but who are in the vicinity of the attacked birds, and they will change by collective intelligence, they will change the trajectory of the flock so that the predator or the source of danger is avoided. Okay, so a few birds may be lost and maybe killed by the predator, but the rest of the flock will actually be able to avoid further damage. Is this concept going through? I mean, are there any questions?
No, sir, there are no questions.
All right, next slide, please. All right, so our objective behind this was that India is planning, many smart cities in 5 years, and security of these smart cities is of great importance. The energy consumption of these smart cities, the electrical energy consumption and other utilities, for example, water, etc., would be metered and actually monitored by a secured meter interface. This is called advanced metering infrastructure with intelligent or smart meters, which would be the key components of the smart city infrastructure. Securing the advanced metering interface is basically the securing of smart energy meters against attacks by people who not only want to bring their bill down, but they may actually attack the meters and make the utility stop functioning, or may cause catastrophic damage to the utility network. So the objective is the detection of attacks in smart meter clusters. So we treat neighborhoods of smart meters as a cluster of IoT nodes using swarm intelligence methods. So the USP or the unique part of this solution of this method would be fast detection of attacks locally at nodes which are not really very computationally powerful. So please note that smart meter processors or CPUs that are included in smart meters are very rudimentary. They are 8-bit or maybe just 32-bit low clock frequency machines, because the smart meter cannot itself consume a great deal of energy. So they are low-end processing nodes. So they obviously cannot execute very complicated algorithms to detect their entropy and things like that. Detect their own anomalies. So can we use collective intelligence like swarm intelligence to detect whether there has been an attack on the on one of the or some of the meters in the cluster of meters? Next slide, please. Next slide. So we built a swarm intelligence system comprised of a swarm intelligence framework, which contains swarm intelligence algorithms, which form a core engine for swarm formation and detection. So it detects clusters and then forms swarms which forms clusters inside the swarm which communicate to each other with each other, and then we have a user interface to just monitor the activity. Use cases: the enhanced security in the advanced metering infrastructure by detecting attacks using swarm intelligence. So the idea is to detect anomaly-based attack detection in IoT environment using swarm intelligence. We tried to develop a generic swarm intelligence framework which can be used for other applications in IoT environments also. And swarm intelligence framework can be adapted to different use cases by simply plugging in these algorithms, this framework, to other application requirements. So the kind of hardware software that we use is we use Raspberry Pi 3s connected to our meters, which have the so-called IoTVT stack. IoTVT is software stack is meant to enable communication between IoT nodes through Wi-Fi, Bluetooth, etc. Swarm is our algorithms contain the swarm formation and swarm detection. So depending on the neighborhood, swarms are formed, and then communication is enabled between agents. We have anomaly detection algorithms, so basically entropy calculation algorithms, and all this is fitted into a framework. Next slide, please. So this picture shows the view. This is a pictorial view of the setup. So the picture on the left shows various houses, each with a meter, a smart meter. The substation is sending out electrical power on the transmission line, the power transmission line, and each of these meters has got Wi-Fi or wireless capability for the reader to be able to read it without physical visit, and using the same Wi-Fi connectivity, the meters can talk to each other. Now, this cluster of 9 meters is actually being swarm of 9 meters has actually been divided into 3 clusters: the blue cluster, the pink cluster, and the green cluster, depending on the connectivity and the proximity. So the nodes that are near to each other form one cluster, so that this can be fast, right? And each cluster is connected to another cluster, other clusters, by means of common nodes between clusters, right? So each of these nodes has a microprocessor, RPi3, connected to the meter, and then the software stack shown on the bottom right is resident on each of these microprocessors, and then each microprocessor calculates its own entropy figures and communicates to all the other microprocessors or meters in the vicinity, in the same cluster. So let's say the four nodes in the blue cluster would be communicating the entropy figures to each other, and then this would be communicated via the common node between the blue cluster and the pink cluster to the next cluster. So as a result, everybody would have everybody else's entropy information. Right. Next slide, please. So as a result, what happens is, whenever there is a change in entropy of any of the nodes, any of the meters, it is immediately known to all the other meters in the vicinity, who can then do various corrective actions quite immediately, because the communication latency is quite low. It is only 1 hop or maybe 2 hops, right? And this can address the problem quite fast, instead of the other case where it would actually have to go back to the data would have to be communicated back to the substation, where the substation would probably run some complex algorithm to detect the anomaly, or maybe even further back from the substation to the main generating station. So this would add to the latency. So we claim that our solution is faster because of the action which is taken in real time at a local level. Right? So the alarm condition can be detected and communicated, and that corrective action can be taken quite fast at a local level. So the capabilities of this this setup are that it's a generic swarm intelligence framework with peer-to-peer mesh networking. The swarm formation is done automatically, as you saw. The blue, pink, and green swarms are formed by distance measures. This can be used in the IoT environment, not only meters, but other IoT environments, like, for example, industrial IoT with mobile robots and drones. And it is easily extended to other use cases because the software is made as a reusable plugin. So its impact is that it can detect attacks without any centralized solutions or a server, a centralized server. Attacks can be detected locally, quickly, with low bandwidth, because a lot of data is not traveling along the network to the back end. So communication is local. Very little computation is involved because each of these nodes is quite a simple computing machine. So this is quite suitable for low power devices like energy meters or smart devices at homes, which are IoT nodes. And this is autonomous, scalable, so you can make the cluster as big as you want, and the alerting mechanism is quite fast and almost in real time. Next slide, please. So the applications that we are suggesting for this, apart from this metering, is, for example, swarm robotics in industrial IoT, or drones in a disaster recovery scenario. So imagine that one drone may not be enough to lift a load, but let's say 20 drones may be able to cooperate with each other using swarm intelligence methods to lift a heavy load, right? You can use it for land survey with a swarm of drones, getting crowdsourced data from audience poll. That would be a software function. There are other interesting functions like which are purely software, like software testing of code in software engineering, image segmentation, data mining, etc. Next slide, please. Next slide. Hello. Next slide, please. Okay, so that is the sum and substance of the presentation. So we have about 10-15 minutes for our question and answer. So we could now take some questions and questions.
Thank you so much, sir, for such an interesting talk. We have few questions from the participants. So the first question is whether these kind of intelligence systems are currently in use, or these are just in plans now.
Well, these are in use, for example, in robotics, right? So there are these swarms of robots in very complex and vast warehouses, like the one, for example, online marketing company like Amazon. So there, what happens is the robots are just given an order to fetch something, and then they coordinate with each other to reach the particular shelf where the particular product is kept, and then retrieve it and then bring it back. Okay, so you can imagine that this cannot be done with without the robots cooperating with each other, because if swarm intelligence types methods were not used, then they would actually crash into each other, or maybe interfere with each other's work. So the way it works out is that all the required products are fetched in the minimum time. This is the optimization it does under the constraint that no particular cluster should collide with any other cluster, right? So this is possible. So one exciting application is in mobile robotics.
Thank you, sir. The second question I'll take up is maximum how many such robots can be clubbed together?
See, that depends on the the strength of your communication network. So we have tried our particular method up to in a test scenario with up to about 32 nodes. Okay, but that was only for the test. We are convinced that this can go up to say hundreds of nodes. Okay, but for robots, I cannot say. But there is nothing that limits it this number except the communication bandwidth, the limitations of the communication. So what you have to do is you have to write your algorithm in such a way that the data communicated by every agent is not a great deal.
Sir, I'm taking up another question. Are these systems cost effective?
They are very cost effective because the actual computing machinery is quite small. Okay, the microprocessor that we have used is very simple, and the power consumption is quite low because the algorithm that is being executed is quite simple, right? So the power requirements are also low. So these are we claim that these are cost effective, right? It's
So
about
there is
as cost.
one more question.
Yes.
So there is actually one more question where they have asked how these systems are helpful in disaster recovery.
All right. So assume that there are two ways of doing disaster recovery. First of all, in disaster recovery, in every affected place, you may not be able to send human agents, right, to do the recovery work. You may have to send in machinery or robots. Now, one way to do this is to send in one very powerful robot. Okay. But then that has limitations because if that robot, the maneuvering of that robot may be quite complex because after a disaster, the topology may become quite broken up, etc. So one single powerful robot may not be able to maneuver itself into the disaster affected area. But if you have multiple robots, then what can happen is each small robot can maneuver itself in coordination with the others to get to the affected area and then deliver the relief. Okay, where it may not be possible for a single big robot to reach. Okay.
Sir, there is one more question. The question is, what are the typical real-time challenges that we might face in order to implement these algorithms for Indian smart cities, and how we can overcome this?
The biggest problem we'll face is the RF propagation, the communication. Okay, because you see, in a crowded city, RF communication itself becomes a challenge because of reflections, then interference and reflections and noise sources. So RF communication would be the biggest bottleneck, and that may limit the range of your solution or your system. Okay, so we visualize that with the arrival of 5G communication, each of these nodes may be now 5G enabled. That would give us more bandwidth, but also give us faster communication with a greater reach. So we are thinking of something like 5G machine-to-machine communication. Other questions?
Sir, yes, sir. Sir, you have used the entropy again and again in your talk. So, sir, what is exactly entropy in the context of this swarm intelligence?
No, entropy is just an index of health. Okay. So each node's health has to be monitored by all other neighboring nodes. Now, in regular use of electricity, if you plot the time series and make its histogram, then you can calculate the entropy of any histogram. Histogram is a probability density function. UDF, you can always compute the entropy of. So the basic idea is that in normal conditions of electricity usage, that distribution of energy usage over many days will have a certain shape and therefore a certain value of entropy. So when the neighboring nodes see that the entropy of a particular node of which they are neighbors is showing an abnormal value, okay, which has not been the case for in the past, then they'll know that there's some problem with this node. Suppose the people of that house go away, then there'll be a drop in the energy consumption. So it'll be an anomaly. Similarly, if somebody tries to do something, say tampering actions on this, similarly there will be a change of entropy. So the time series will change, and therefore its PDF will change. This is what we try to detect. This is what the neighbors will try to detect. Okay. So effectively, we are trying to characterize the probability density function of the energy consumption of every node as entropy. Does that answer your question?
Yes, sir. Thank you, sir. Sir, one more question I have. So, sir, regarding this communication between the swarm nodes. So, sir, are you also working with this newly developed protocol called LoRa protocol?
No, we were not working with LoRa. For our case, we were working with Bluetooth and Wi-Fi. Okay. LoRa is eminently possible. LoRa is, for example, a challenger to 5G. Okay. So, but our particular method is agnostic of the actual communication protocol. It is equally applicable to 5G as well as LoRa, because the communication is abstracted for us. I showed you a word IoTVT a little while back. So IoTVT actually hides the complexity of the communication network from the programming on top. Okay. So whatever communication protocol is used in the physical layer or the communication stack, our algorithm is agnostic to that. Okay. Is that clear?
Thank you, sir.
Thank you so much, sir, for this interesting talk. With this, we have completed the Q&A session for this talk, and now we will move forward with the next talk.
So thank you for the opportunity. And Dr. Das, Dr. Manna, thank you for hosting me. And please give my regards to Professor Iyer.
Sure, sir.
May I disconnect now?
Yes, sir.
Okay, thank you.
Thank you so much. Now we will move on to the next talk. This talk will be delivered by Dr. Rakshveer Jasra, who is currently working as a Senior Vice President, Reliance Technology Group, Vadodara. He is an adjunct professor, RMIT Melbourne, Australia. He is also Honorary Professor, IAR University, Gandhinagar, and Honorary Professor of Centre for Nanotechnology, IIT Guwahati. He has more than 300 research papers, 180 patents, out of which 63 are US patents. He has been awarded with Golden Peacock Award 2019, 8th National Award for developing novel polymer for high performance automotive tire application. He has also won Federation of Gujarat Industries Award for Excellence in Research in the year 2015. He is also a fellow of Indian National Science Academy in year 2019. Sir, I request you to take over and start with the presentation.
Are you able to hear me?
Yes, sir, we can hear you.
And you can see my presentation.
No, sir, presentation is not visible. It's uploading.
Network.
So now we can see it.
Okay. Good evening, everybody, and thanks for kind words. So what I'm going to do next 40 minutes is take you through some area of catalysis, which is a very important process.
Excuse me, sir.
Yeah.
Sir, could you please maximize the slide?
Okay. 1 minute.
Thank you, sir.
Will take a little time. I'll do it. It is taking some time. Okay. I'll continue, but I think it's some problem is there right now. Just you're able to see the slides or not? Hello?
Yes, sir, the slides are visible.
I think I'm finding some difficulty here. 1 minute. It is my PPT is not responding. So I can continue. Let it take a little time. I think it will. See, this area of catalysis is very important. Hello.
Sir, please continue.
My slides are not moving. Some issue. I don't know. Maybe the network issue is there. Hello. Should I log out and then join? There are some issues. My slides are not moving. Yeah, now.
Sir, could you please just log off and then log in again?
No, let's see.
Yes. Sir, it is okay now.
No, it's okay, but second slide is coming now. Yeah, now.
Yes, sir.
This is my disclaimer that whatever I speak here, these are my views, nothing to do with my company, and I am responsible for all the statement, not Reliance. See, this presentation outline is I will spend one slide on why catalysis, how catalysis is important to chemical industry and what role it really plays. Then I will spend some time on explaining how nanomaterials are related to catalysis and how they are really bringing paradigm shift in the concept of catalysis. And after that, I will show you like a few developments on nano-engineered catalysts which has been done in Reliance on a commercial scale. This is the outline of my presentation. Now, role of catalysis in chemical industry is very critical. In fact, chemical industry and catalysis have got symbiotic relation. One helps the other to grow. Now, if we really look into the catalysis, it is 90% of the manufactured good in chemical industry today. We are seeing the role of catalysis at some stage or other during its manufacture. And total, it has really enabled, the catalysis really enable around 15 trillion revenue annual in the world. It's a very important technology, catalysis technology. You can see as far as the chemical industry is concerned, environment is concerned, even pharmaceutical industry is concerned, materials production is concerned, it really plays a big role. And 80% of the added value in chemical industry is based on catalyst. What we do in chemical industry, typically we value add the raw material from a low value to high value product. And 80% contribution really happens from this thing. 20% of the world economy depends directly or indirectly on catalysis. This just giving some numbers which are very important to know how the catalysis plays a big role in the chemical industry. Catalyst as such, if we look into the market value of catalyst which we use, it is only $32 billion. market.
Excuse me, sir. Sir, sorry to interrupt, but I think the slides are not changing.
No, I'm only on the slide number 4. Catalysts in chemical
Sir,
industry.
we are still on slide number 2. Sir, I think it's not changing.
Now, 1 minute. This is to now change?
No, sir.
There is, I think, network problem there. Network is fine.
Sir, maybe you can unshare it and share it again, sir. Sometimes it happens in Teams.
Okay, I will go. I will again upload my.
Just request control.
Okay, now. Oh, you are able to see anything or not? Now slides are visible?
No, sir.
Not yet, sir.
I don't know. I am finding it very tough. It's never. Still not seen by anybody. Hello?
No, sir.
Okay, then I will do something. I will again go out and join again. I will upload again. Okay.
Yes, sir. Thank you, sir.
Now you are able to see? Still not. Seen or not? Hello? You're able to see my slides now?
No, sir. Sir, is it possible that you can mail us these slides so that we can
That will
share
also
it
take
from
time. That will also take time. I can do that because the slide, this file is big. If internet is slow, that also will take time.
Dr. Jasra, you just Deepankar here.
Yeah?
You just log off once and log in. Perhaps some of the other things are there in your computer that is coming on the way. So you once log off and log in, I think it will start responding. This happens in MS Teams.
Hello?
Yes, it is coming.
Now you are able to see?
It is visible. Yes.
Okay, if I move to second, no.
It has moved, yeah.
Okay. So I was on.
This is on the first slide.
Okay, this is my first slide.
Yeah.
I'll start again. Sorry.
No issues.
This is disclaimer, and it means whatever I say, these are my views and not of Reliance. I am responsible for those. So as I said earlier, I will go through this presentation outline where I will show how catalysis is very important and critical to chemical industry. Then I will show how nanomaterials are linked to catalysis. And then I will show you two examples where we have developed nanocatalyst and on a commercial scale we are using in industry. Now coming to the role of catalysis in chemical
Dr.
industry.
Kasra,
Yeah.
sorry to interrupt you.
Yeah.
You go back to your normal mode. Don't maximize it. Perhaps the slides are not changing here. You please press escape. Please press escape and get back. Slides are not moving, actually.
Now what
Yes.
slide are we seeing? Able to see slide number 4, like catalysis in chemical industry?
No. Yes, now it is okay. Please go ahead, this mode. Thank you.
Okay. So here if you see the role of catalysis, in fact 90% of manufactured goods in chemical industry would have seen catalyst some stage or other during its production. So it's so important. And around 15 trillion revenue is created in chemical industry because of catalysis. It is such a critical and impactful technology. You can see 80% of the added value in chemical industry is today based on catalysis. And it's growing also. And 20%, it is estimated 20% of the world economy depends directly or indirectly on catalysis. When I say catalysis, it means all heterogeneous catalysts, homogeneous catalysts, and also biocatalysts, that is enzymes. Now today the catalyst market, if I just see the value of the catalyst, the manufactured catalyst value is around $32 billion. But more than this, what is important is the value they create. 100 to 4 times its own value is created by the catalyst. That's why the catalysts also are known as performance chemicals, because whatever its value of catalyst is $1, but it can create value of $100 to $400. That is the beauty of this material, performance material. And today most of the processes which are used in chemical industry are 80% are heterogeneous catalyst, 15% are homogeneous, and 5% are biocatalyst. We are seeing more use of this biocatalyst and homogeneous catalyst in industry, but because of the easiness of separation of heterogeneous catalyst, I think still the chemical industry is dominated by heterogeneous catalysis. Now, the last point which I have written is catalysis is also a major socio-economic importance. This is very important. It's not only it is relevant to the chemical industry, catalysis is also very important to society. If you look into environmental issues, many of the environmental issues are really solved by catalysis. And even if we look into some major problem last century, major problems of food, health, or mobility, we will see that catalysis has played a big role. If I look into the food industry, the availability of ammonia, urea happened only because the catalytic process for synthesis of ammonia emerged in early 1900, which made the whole fertilizer industry to come and solve the food problem. Similarly, in the mid of last century, the mobility, because of the availability of gasoline, diesel, and aviation fuel, the world has really become very mobile and connected. On health sector, if you see all the drug industry, pharmaceutical industry, and chiral drugs are more important. If you see, all because we could have very good catalytic processes, especially for chiral catalysis, which has really brought the chiral drugs into the market at a lower prices. Similarly, the environmental issues. Today we are facing a lot of environmental issues. There also this catalysis has played big role. And when I look forward, future problem of the society, like we are now at fossil fuel free energy. We are all thinking hydrogen fuel cell or carbon free energy. You will see without catalysis, none of these things are going to happen. Same thing on new materials. When we want to develop new material, catalysis is going to play a big role. So catalysis is not only for chemical industry, it is also very important for whole society. That's why it has got huge socio economic impact. Now I come to this next slide. I come to this how nanocatalysis and nanomaterials are linked. Now my next slide is seen. Hello. Hello.
Yes, sir. We can see it.
Now see, catalysis gets linked to nanotechnology and nanoscience because of the catalytic material. Now, nanoscience and nanoengineering last 20 years has helped really catalysis in a big way. I have been practicing catalysis almost now for 30 years. I have really traveled through this whole journey. Now, the enhanced understanding on the relationship between catalytic performance at atomic level structural details really has become possible. When I just joined, maybe 80s, early 80s, we used to say catalysis is more of an art than science. But today I can tell you it is no longer true. It is a lot of science and less of art because of this whole nanoscience and nanoengineering developments which have happened. And also we are today able to engineer the size, shape and the facet of nanoparticles really to improve the catalytic conversions, catalytic selectivity, which is a very big step forward in designing new catalysts. I'll show you a few examples also. And also we are seeing big merger today. Catalysis and material science are literally merging. Mostly the catalytic material today use all the techniques which are used by the material scientists like electron beam lithography, atomic layer deposition. All those techniques are now really becoming important in the area of catalysis also. So some of the attributes which nanomaterials bring in the catalysis, because of this, some of these interesting features when you go to nano domain, large surface to volume ratio. Catalysis is a surface phenomena. If more surface is available, the activity goes up. Electronic effects, that also affects the electronic state of a metal, catalytic metal, when it is in a nano stage. So confinement effects we see. Some of these unique attributes which happens to materials on a nano domain, that also is very, very useful to catalysis. So today we have got three types of nanomaterial which are extensively used on commercial scales in the area of catalysis. Number one is nanometal particles. See, most of us knows the platinum, palladium, silver, gold, nickel, cobalt, chromium. These are the metal, transition metal and the noble metals which are used as commercial catalyst. Earlier also people were making these catalysts which were nano size, but the control on the size of the nanoparticles, shape of the nanoparticle which was used as a catalyst was not there. But today we have arrived in a position where we can control the size of these particles, the shape of these particles, also the facet of these particles. So this is one area in which nanotechnology really has made a huge impact on the nanometal particle based catalysis. Second is the nanostructured nanocrystalline material. Most of the time we use metal oxides as a support for these nanoparticles. Nanoparticles are supported on these metal oxide supports like zirconia, alumina, silica, titania or ceria, which I have shown here. Now these materials also you can produce in a nanocrystalline shape, like in nanocrystalline, not a bulk material. You can go, the grain size can be controlled. That also helps big way to improve the activity of the particular catalyst made from this support as well as the nanoparticle. Now the third material which has huge impact, in fact tremendous impact has been made by nanoporous material. When you load these nanoparticles, you always need the porous material. Porous material means they should have a lot of porosity. There should be nanopores available in the material in which the particles, this active metal component is loaded. We have seen this emergence of these zeolites, which are aluminosilicate crystalline material. They have the pore size less than 10 angstroms. And those materials and some of the clays, which also are two-dimensional porous materials, and some ordered silica. And recently we have seen this very, very large family of metal organic frameworks. These are all porous materials in which you can do the reactions, and they are of nano dimension, of molecular dimension, and they also influence the selectivity and the activity of the catalyst. So these three materials, one is nanometal particle, second is nanocrystalline material, third is nanoporous material. They really connect the nanotechnology and the catalysis very well, because all the catalytic processes are developed on these materials. Now I'll show you few examples how the size of a particle can really influence. Here I have shown you gold on alumina catalyst, and if you see, the moment you go to 3 nanometer size of gold, 3 to 4 or less than, you can say 4, the activity rate of the reaction is very high. It really goes up exponentially. And though we are in nano domain, when I say gold in 7 nanometer or 8 nanometer, then also I'm a nanoparticle I'm using. But if you see this graph, it is not very active. So it is only showing very large activity when it is around 3 nanometer or less than 4 nanometer. You can see here the activity of this gold is very high when it is in this domain. So it means what? It means normally we say any particle which is less than 100 nanometer is a nanoparticle. That is true. But to be catalytically active, that particle, it's not necessarily that when you go to 10 nanometer, 20 nanometer, it will become very active catalytically. You have to go to specific size for a specific metal where it is showing maximum activity. For example, in this case gold, if you really want gold in nano size, then if you are in 3 to 4 nanometer size gold, then only you will see very good activity for carbon monoxide oxidation. It means nanoparticle size really has got a significant role. That is one. Secondly, it is very important for us to know for each metal where it shows maximum activity for particular reaction. It's not that when we make any nanoparticle, it will show very good activity. You have to know. And why it is so? It has been now using this scanning tunneling microscope. They have shown that when you are in nano domain, then these atoms of gold, they'll be maybe sitting on corners, they may be sitting on edges, or they may be on the surface. But particularly for gold, when really you are in this less than 10 nanometer, when you go to size where less than 4 angstrom, then you will see more atoms, gold atoms at the corner or the edges. And that's what makes those corner atoms and atoms at the edges gives them higher activity, because they are not part of that bulk and they are not coordinated fully. So they are active metals, and that has been really shown very clearly in this data. And this is really, now you imagine this type of understanding available to a catalyst scientist. When he knows, when I make this nanoparticle of gold and when I go to 3 to 4 angstrom at nanometer size, then I will see the atoms more on the corner or edges, and they are really giving activity. Is a huge knowledge base, because you can use this type of knowledge to really tailor make or design a catalyst for desired activity. Only problem today is how to synthesize the materials where you can maximize the atoms of gold at the corner or the edges. That's where what I said, the new material synthesis technology are becoming now more and more relevant to catalysis, because we have to have that type of technology available so that I can put more atoms on the corner and get the more activity. So this is one very good example I've shown where the particle size is important. And this is another example where the nanoparticle size also is very important. For example, in platinum, here doing this hydrogenation from pyrrole to pyrrolidine to butylamine butane. This is the all possible reaction, and you can see even if as the size goes up, the butylamine is found more at higher size. When the size is small, you don't get butylamine, you get the other compound. So here also, by this type of knowledge base available to you, you can always see what is the metal particle I should really use for making a catalyst to make this catalytic conversion or the organic transformation selective. Second now point which has also been realized when we talk about nano metal particle is the shape of the nanoparticle also influence the activity significantly. Now here they have made platinum nanowire inside a porous material FSM16. This is something equivalent to MCM47 silica, which is a mesoporous silica, ordered mesoporous silica. Now you can make the spherical particles by using certain synthetic methodology inside the pore. You can also make the rod type or wire type nanoparticle, as I have shown on the left hand side. We have the platinum inside the this thing, and they have also checked the formation of the nanowire inside MCM through TM. Now important is when you have got platinum nanowire inside the FSM16, the activity is order of magnitude higher compared to nanoparticle, spherical nanoparticle, under similar condition for carbon dioxide in water gas shift reaction, the formation of carbon dioxide. So this is also very, very important information, because this tells you nanoparticle size is important in deciding or determining the catalytic activity, but the shape is also very important. Now different when I do benzene hydrogenation, you will get cyclohexane as well as cyclohexene. But if I use this platinum 100 facet rich material, then it is a complete hydrogenation. You don't get cyclohexene. Now, when I am doing hydrogenation of benzene, formation of cyclohexane is very important. If I can make selectively cyclohexane, I can really add good value to that product, because it is further used for developing for making some products. So this type of information is also very, very valuable. So when I'm making a catalyst, if I want some cyclohexane to be formed, it is very important that my platinum should be in certain nano range, it should be in certain shape, and also that facet, desired facet, should be maximized, exposed to the reactant. Second example is on, again, for same reaction, if either two shapes, cube or octahedra. Now, if you have got cubo-octahedra, then you can get some cyclohexene. But if it is only cubes, you don't get cyclohexene. So these few examples, there are many examples after even this work. A lot of examples are there. One can spend, 40-50 minutes only showing various examples. But I'm just showing some representative example to you, so that we realize that when really we develop a catalyst, the facet of your metal particle which we want to be exposed is very, very important in making a catalyst. So this is this type of information when we say metal catalysis is really the insight or the understanding has come only because of the ingress of nanoscience and technology into catalysis, and it has really enriched the area of catalysis. Now I can show you, if you really link it to the in our society, one catalyst which all of us use in our cars is auto three-way exhaust catalyst. This is a very important catalyst. If it is not used in catalytic converter, which is any car which comes on the road, even in India today, has to have this catalytic converter. It has platinum rhodium catalyst inside it. Why it is called three-way? Because it converts hydrocarbon to carbon dioxide and water oxidation, carbon monoxide, which is produced during this burning of fuel. Hydrocarbon is also produced, which is not burned fully. Then carbon monoxide gets converted to carbon dioxide. It should not be emitted to atmosphere because it's a poisonous gas. And NOx also gets converted to nitrogen and CO2 by reaction with carbon monoxide. So this catalyst has to do all these three reactions. Then only it is really effective catalyst. Now, you see I want to show the stringent requirement of this catalyst. This is European standard, and our Bharat 6 standard is also very close to European standard. It says the carbon monoxide should be less than 10 ppm. It means most of the carbon dioxide which is generated, it may be as high as 10,000 ppm should get converted to carbon dioxide. Similarly, this hydrocarbon should also go to less than 1.5 ppm, and NOx should go to less than 0.3 ppm. Other two things also are there, sulfur and fine particles, soot. They are different catalysts, but this three-way catalyst only focuses on hydrocarbon, carbon monoxide, nitric oxide to nitrogen. You can see the demands on which. Second demand is shown in really this. When you start the engine and when engine is full capacity burning, you can see the conditions, temperature conditions are very different. It is from ambient to very high temperature. And if you see this graph, most of the chemical productions, chemical industry, all the chemical which made lies within this range only. You can see any I've shown propylene oxidation, phthalic anhydride. Most of the chemicals are produced within this range only. And this catalyst, three-way catalyst, has to work almost entire the temperature range and also the concentration range, very concentration range, and very demanding requirement, because it should work when your cold engine is idling and just cold start. Then also some hydrocarbons produce other thing, it should convert. And it should also keep on doing similar work when we are at very high temperature inside the engine. You can see these are the demands. Now this type of catalyst is working, and also it is not only this should work under different very diverse condition. It should also work for years. It should not go bad within a year or two. It should work for many years. That is also demanding. So this type of research is really understanding of this particularly three-way catalyst is possible also because of some of the very well advanced techniques available through. One is high resolution TEM, second is also they are preparing single atom of platinum, single crystal of platinum, and then making like FCC 111 here shown. And then they are doing this lithography, IHL electron beam lithography, and by which they are preparing the single crystal and then trying to relate the property of this phase, whatever they see, and performance of the catalyst, this type of thing. Once you have this understanding, then really we'll be able to develop even a still robust catalyst. So what I wanted to show you, the requirement of society to run a car on catalytic converter, and very diverse or very wide range of requirement on the catalyst can only be met if we really understand this catalyst on an atomic scale, how it performs, what are the active facets, what is their active shape, and that type of things is able to, scientists able to do in the lab only because some technique like electron beam lithography is available to them. We have got high resolution TEM available to us, so where we can see these particles very well. So this nanoscience and nano engineering really has helped, as I said, on very big. Anybody who has done chemical engineering or chemistry, he will know the earlier times when we studied the catalysis means kinetics. It only enhances the kinetics of a reaction. So we will always study the kinetics of the reaction, and then we will see, we know the catalysis and kinetics are very deeply linked. We will know the catalysis very well. But I think time has changed now. Now, because of this type of understanding, which I have deep diving of catalysis, which I have shown you, people are talking of kinetics is important, but we are also talking of electronic effects and really making now single atom catalysis, cluster catalysis, all those things. You will see if you go to any good journal today, JACS or other, you will see a lot of work on single atom catalysis, metal cluster catalysis, high entropy metals catalysis. Those type of things are now becoming more and more important, and which are really going to change the whole area of catalysis. It will take it to really higher level of science and technology. So what I can say that earlier, maybe 80s or before, whatever catalyst was manufactured in industry, and even the people working in the laboratories making catalysts, it was more of incident. They have learned the making of catalyst through like tradition. You make in certain way catalyst, you will do some support selection, some method of metal deposition, like maybe wet impregnation, incipient wet ion exchange, then certain way of drying and oxidation and activation. It was acquired through knowledge, or will learn from others or your own experience over period. If you make this whole thing a catalyst in certain fashion, following certain conditions, you will end up with a good active catalyst. That is the type of catalytic manufacturing was done. But this is really changing very fast now, because now nano catalyst preparation is different. It is now you can design the catalyst, because support selection is okay. You can select the good support, nanocrystalline support with non-porosity, pore size distribution, maximizing micropores or nanopores in it. Then you can make nanoparticle synthesis. You can now synthesize the nanoparticle with desired nano size, particle size, desired shape or facet to some extent. At least facet still we are away, but size and shape now we understand. Then we can really make those nanoparticles. Then you can incorporate those nanoparticles in the support by known methods, and then do activation. You will get the most of the time whatever catalyst you want, you can really make and manufacture and really use it. So this transition from incidental to design approach in catalyst preparation has only happened because of the advent of this nanoscience and nanoengineering in the area of catalysis, which is a paradigm shift, I can tell you, because catalysts are now designed rather than discovered, which is a big change. And I have shown you how important area of catalysis is really to the our society. Now, I think I will now show you two examples where we have done some work in the area of nanocatalysis by using some aspects of nanoscience and nanoengineering and develop these catalysts. Now, in refineries as well as petrochemical, this reforming is a very important chemical process. Reforming means conversion of naphtha. Naphtha is produced from crude oil by after doing this vacuum distillation or atmospheric distillation. Then that naphtha is converted to either gasoline, which is used in most of the automobiles, or you can convert them to aromatics, which are used for production, a lot of products like polyester and others. Now, we are the largest reformer in the world. Reliance has got the largest CCR reforming. We call it continuous cyclic reforming, and the UOP calls it platforming, but this is reforming, where we convert the naphtha to aromatics, because aromatics are the one which we want, because we produce polyester, biggest producer of polyester in the world, and we need paraxylene. So paraxylene will be obtained after converting naphtha to aromatics, C8 aromatics. So what we do, we use this catalyst, around 540 metric ton catalyst we use in Reliance, and it's very expensive. We spend almost 100 crore rupees on this catalyst every year. Now this catalyst converts our naphtha to aromatics by variety of reactions. Some of the reactions like chemistry, very complex chemistry goes on this catalyst. Dehydrogenation of naphthenes, isomerization of naphthenes and paraffins, dehydrocyclization of alkenes or paraffins, hydrocracking occurs, demethylation occurs, dealkylation occurs. Some of these reactions are desired, some are not desired. Now you have to develop a catalyst which can do all these activity, and it should do more of those activity which you want it to do and less of those activity which you don't want it to do. Like we don't want it to do hydrocracking, demethylation or coke formation. We want it to do more of dehydrogenation, dehydrocyclization or isomerization. Now this catalyst which normally used is platinum and tin on alumina. It means you have to put platinum, you have to put tin on alumina support. So there has to be specific alumina support having some acidity, and there have to be platinum and tin in certain size and shape. So we have been working on this from 2012 on this development of this catalyst, because as I told you, it is very, very important. We have the world's largest reformer with us in Jamnagar. So we made this catalyst, many formulation. Ultimately, first time in the world, we have been able to develop chloride-free this CCR catalyst. Chloride-free means normally everybody in the world use alumina, which is chlorided to provide acidity, and on which they put platinum and tin. Now we have put no chloride on this alumina, which is a big development, because when you put chloride downstream unit, chloride can be corrosive, a lot of problem comes. And chloride-free CCR catalyst is a dream for everybody. So we developed. Now how we did? Here we have really used our understanding and knowledge of nanoscience. What we did, we said we will not put any chloride, but we will put some oxide layer on platinum and tin after loading on alumina, and that should be acidic, and also that layer should be only few nanometer thick layer of that metal oxide which has acidity. So acidity will come from that, and when that nanometer thick sheet is put on platinum and tin over this our first initial catalyst, then it helps. How it helps? It doesn't allow platinum and tin to sinter because the temperature in the forming is 540 or so. We go as high as 540. So metal movement happens in metal centers. So nanoparticles become bigger particle, and that's how it got deactivated. Second is there is a coke formation, carbon formation. So what we did, when we put this nano size thin sheet of some metal oxide on our catalyst, it doesn't allow platinum and tin metal particles to coalesce because of sintering, and also the coke formation is less. And this is very cleverly done by atomic layer deposition technique, which is used extensively by material scientist people. So we have put some metal oxide on it using this particular technique, and you can control how many layers you want, atomic layers, like you can put 30 atomic layer, 40 atomic layer, whatever you want, so the diffusion of the reactant and products to platinum and tin is not affected, but the sintering is checked. This is what we did, and we were very, very successful in really developing this catalyst. And then we have worked very hard. We have a pilot plant where we tested this cattle under actual process condition, which we use in our plants. And also we use the actual naphtha. See this, if I use some compound, synthetic compound in the lab, that doesn't really give a real picture. So we brought the naphtha, which has all the impurities in it, which is actually used in the plant. We have used the naphtha, and using this thing, we have shown. Now you see this number, you just see the blue line and the black line. Black line is without the atomic layer deposition, and blue line is with atomic layer deposition. You can see the activity and the stability of the atomic layer deposit catalyst is higher compared to blue line. And here few percent, 2.5% higher liquid yield means millions of rupees to us because our plant is very big. So we got 2.5% higher liquid yield and stability was 1.2 times higher stability, 65% less coke. It means sintering is not happening and also coke is not forming and we are getting better yields. It means a lot. So this is what we could do. And now we are scaled up this catalyst to 1 kg scale. Now in where we have gone to 10 kg. And we are now in dialogue with some companies to manufacture this catalyst on tons of scale so that we can put it in our plant. So this is how you can really make a big change in your catalyst if understanding of the particularly the whole ability to put a nano sheet on your catalyst surface to check the sintering is the key development which we have done. The second catalyst which we develop is related to zeolite, which is a nanoporous material. As I said, zeolites are luminosilicate which have got uniform sized pores and they're all interconnected pores. And most of the pores, or almost all zeolites pores are less than 10 angstrom. So it means your molecules are also, most of the molecules are less than 10 angstrom. So they can be really selective at a molecular size or shape level. So that's why they are also called molecular sieve. And they also diffusion also is here in configurational diffusion because of this small size. And they're very close to size of the molecule. The pores are of similar size. So then diffusion is little different here. So we can really create selectivity or selective catalyst using zeolite because of their size and shape, which is close to molecule. And then also because of diffusion. And by exploiting this concept, we developed a catalyst for making paradiethyl benzene from ethyl benzene or mixture of, let's say, C8 aromatic, ethyl benzene, metaxylene, everything is there, but we want only ethyl benzene to react and give paradiethyl benzene. And paradiethyl benzene is very important chemical when we make this polyester. Polyester needs paraxylene, and paraxylene production needs para-DB because this is separated from C8 aromatics paraxylene by adsorption process, and for dissolving adsorbed paraxylene you need para-DB. So this is also very important. We want to produce para-DB, and since we need, and as I said, we have a second largest producer of paraxylene in the world now. And that's why this material is important to access. We produce around 4.3 million metric ton per annum. 11% of the world capacity of paraxylene is within Reliance, and which is very important. So what we did, now the pores of our zeolite, zeolites are nanopores. The zeolite which we use is having elliptical pore opening 5.6 to 5.2 angstrom. Now opening of this zeolite pore was done in such a way that only paradiethyl benzene can come out and the ethyl benzene can get into the pores. All other isomers or any other similar compound form cannot get into the pore. Like here I have shown, here we put ethylene and ethyl, of course here should be this ethyl benzene. Ethyl benzene, ethylene will go into the pore. You will get all these three isomers. But what will come as a product is only paradiethyl benzene because others, because of this non-symmetry, cannot come out of the pore. We had changed the pore opening in such a way. You see, the pore size is only 5.2 into 5.6 elliptical. Only fraction of angstrom control of the pore so that only paradiethyl benzene is coming out. That's what we did. You can see this red circle here. Red circle here, this is the pore openings of the zeolite, which is our catalyst. This we have controlled by few fraction of angstrom, maybe 0.2, 0.3 angstrom, by depositing some inorganic material on the pore very cleverly. This is a really nano engineering of pores on practice in a commercial scale. So this really made we could use a feedstock which was not pure ethyl benzene, which was available to us as a mixture of C8 aromatics. We said we'll use it because only ethyl benzene can get into the pores. and whenever inside it is producing other isomer, but only para-diethyl para-isomer is able to come out, is able to diffuse because we have restricted the pores. All other acidity and everything of the zeolite is same, whatever is people use for this particular zeolite. This is ZSM5 zeolite. So this really made us to have 3 selectivities. So our catalyst is reactant selectivity, like it only allows ethyl benzene to get. It is also product selective, like only para isomer can come out, and even the transition state which is formed is also very selective. It can't form like multi-alkylated compound because the pore size is restricted. This is a rare example where all the 3 selectivities are really made possible in one catalyst in the world. There will not be many catalysts. And you please remember, we could do this. One is of course acidity control of the zeolite by controlling silica alumina ratio, but most important step was controlling the pore opening. And we are done this on tons of catalyst scale, not only small few grams or few milligrams. We have done on a commercial scale where we have produced 7-8 tons of this catalyst. And 22 steps, I can tell you, for just controlling fraction of angstrom of pore opening, there are 22 steps we have to follow for getting really. And this catalyst, now we had a plant, our own plant in Hazira, where 5,000 ton per annum commercial production of para-diethyl benzene is happening. We are the only company which is producing para-diethyl benzene in the world by using catalytic route. Other people only do through separation of mixture of para, meta, and orthoisomers. So this is, and we are able to get very high purity para-diethyl, 99.2 plus purity we are able to achieve. So this also could have been done because of the really this pore engineering at a nanoscale and availability of clever chemical reaction on the surface of zeolite, which really made us to do that. We were able to do successfully. And we have developed a few more catalysts using this concept. We have developed few absorbents also using this pore engineering concept and commercialized. In fact, one catalyst for toluene methylation, we developed similar concept and we have sold that technology to US GTC company. We didn't that time commercialize within our own company, but we have sold the technology. Then they have commercialized this in China. So this type of things we are able to do now because of the knowledge of really engineering, science, nanotechnology, science and nanotechnology. So I just want to end at this stage with the few conclusions. Like catalysis plays a key role in growth and sustainability of chemical industry and also society. All your environmental issues today and even the food and health related pharmaceuticals, materials also, catalysis is the key. If you see any polymer synthesis today, catalysis is at the core of polymer productions. Any polymer you take, whether it is a bulk polymer, whether it is a specialty polymer. Then nanomaterials and deeper analytical and synthetic tools are transforming catalysis from art to science. As I told you, availability of some of these high-end instrumentation, analytical instrumentation and material synthesis instrumentation are bringing a big change in the area of catalysis. And now nanoscience and nanotechnology is providing, has really made catalyst scientists to custom design active sites, site environment, and perfect selectivity and desirable activity. We are now even the heterogeneous catalysis, people are approaching the site, active site design and environment like what homogeneous catalysis people are able to do by putting a metal and putting some ligand around it. Even heterogeneous catalysts are beginning to really get into that type of closer to that approach. So model nanocatalysts are likely to be prepared in future using electron beam lithography, spin coating, CVD, self-assembly, ALD. These are the most of the time you will read material science scientists. He will be talking about these terms, but now all catalyst people also are beginning to work more and more on that. And there are many metal nanocatalysts, engineered zeolites now, which have been really commercialized after making use of nanoscience and nanotechnology. So I think with this I would really end, and I am really thankful to all organizer of this conference, and I am also thankful to Professor Uttam, Dipankar, Arun, and also all other my friends in Guwahati. So I'm very happy if any question or any query is there for you to ask.
Thank you so much, sir. Thank you so much, sir, for this informative talk. And we have received some of the questions from the participants.
Yeah.
So we will have a short question and answer session.
Okay.
Question is, nano catalysts are structured or unstructured?
Nano catalysts are structured. All catalysts are structured. See, like what is a, let's see, when I say nano catalyst, I'll have a nano metal particle, let's say platinum based hydrogenation catalyst. So you have to have a platinum, then you can't use platinum metal as such. This platinum is dispersed on a high surface support. So you have to pick up a support on which you have to disperse as small as nanoparticle. If I can go to atomic scale, wonderful, but it's very difficult to do that because they are not stable. So if you can reach few metal clusters, then still better, but that also is still not easily possible. That's why we go to nanoparticle. If you can go to 10 nanometer or 1 or 2 nanometer, you will get better activity. So this structuring is required. Otherwise, you cannot get a good catalyst.
I would like to ask Akshay sir to ask his question.
Sir, nice presentation. It has taken us to a very inspiring journey of catalysis. I had one question. If you are to synthesize parathymine is also a very value-added chemical. Would the zeolite port still allow the synthesis, or a different route is preferred for that?
No, zeolite will work. Zeolite will work. In fact, parathymine separation of parathymine from mixture of ortho, meta, para is done using zeolites. So we can also we have to know thymine is, if we have to do some alkylation other thing, then we can select and even tailor make the catalyst so that we can get the paraselectivity.
Okay. So maybe I think parathymine would be easier, right? Like it would sort of the alkyl groups would sort of bend inwards when they have been pulled out of the zeolite channels, contrary to the ethyl group, wherein ethyl group could wobble on either sides about the benzene axis.
I think some people, I can check, some work has been done on that parathymine synthesis. Separation I know because I have seen those papers when we wrote a review. But production also, there must be some paper. You can check and we can share also on that.
Sir, actually, this slides on this platinum catalyst, chloride-free platinum catalyst, were also very interesting. I was wondering if these platinum catalysts are like sensitive in the sense like naphtha, though it has very low affinity, but some quantities of water cannot be avoided. So are those catalysts sensitive to moisture and oxygen?
Yes, they are all sensitive to any polar compound, see like sulfur and nitrogen compound. So there are specification. When we use naphtha, there are specifications. You have to have naphtha with those specifications, other catalyst will die.
Okay. So that naphtha has to be subjected to a
certain amount is allowed depending on the catalyst, but there are specifications.
Okay, sir, one last question. Now that we are on a nano platform, and that you said that there is a lot of promising avenues that are open for nano catalysts. Typically, this nano catalysts, they are prepared on a very small scale. But on a industry for this large scale production, because I think that they are used on at least on a quintal or ton scale catalyst. Are there any industry that are pursuing such huge amounts of nano catalysts, or it is still in the lab scale?
No. See, what I'll tell you, Akshay, this catalysis, in fact, is always a nano science. If you see,
yes,
essentially a nano science, because your catalyst, when I make any particle, it has to be nano to be active. Only now, because of the understanding available, we are able to really know when I'm making a catalyst, which is very palladium catalyst. I know my catalyst is so many nanometer. Now, because I go to HRTM and then measure the palladium size. And now, what is happening when you manufacture this catalyst, those methodology of making this nano metal particle on the support, so that you get more and more dispersed and nano size particles are emerging more and more. Like atomization. See, when I'm putting platinum on my alumina, earlier, okay, we were doing dispersion and rotating. Now people are doing atomization of chloroplatinic acid, as fine as you can make, and then spray on your support. And when it gets into the pore, those particles will be very small. Or if you can use some other chemical along with your, when you spray metal, that it keeps it little apart. It doesn't allow metal particles to coalesce and make bigger. They remain in nano domain. That type of now understanding is increasing. And this is being done on a commercial scale. If you see, putting metal on support, these technologies are quite now advanced and done on big scales.
Anyways, very nice, sir. I will further discuss with you later, and I will let others ask.
Yeah.
Thank you, sir. Thank you very much.
Welcome.
Now I would like to request Professor P.K. Giri to ask his question. Sir, could you please unmute yourself?
Yes, yeah. And it's very nice elaboration on the industry-related catalyst. Thank you for your nice talk. So I am basically a physicist, and did some catalysis work. So my query is about the techniques of growth, like Dr. Akshay asked about this, and which is the most industrially relevant technique for your application for the growth of these catalysts, supported catalysts? Because you talked about these ALD and new techniques, CVD, etc. So for this metal catalyst, is ALD used, or that is a future technique?
See, ALD is still not used on a commercial scale, and we only demonstrated on a little big scale that, see, because whatever material science people are bringing those techniques, and the catalyst manufacturing company will take time. And the moment you see the benefits by using the technique and bringing selectivity conversion to the catalyst are higher than spending money on that new technique, people will go into it. But I think ALD will come faster, because
which material people have used for using ALD? Which catalyst material?
See, I'll tell you. Suppose now most of the catalysts used for, let's say, hydrogenation, we use palladium or platinum on aluminum. So which are, we don't want them to get coked fast or sintered fast. So if I can have atomic layer deposition, maybe few nanometer thick layer, which doesn't affect the diffusion of reactant and product through it, then this catalyst will last forever. The 2 years, 3 years, if I have to throw this catalyst or activate this catalyst, I can extend the life to 5 to 7 years. So there are some catalysts, I'll tell you, when we do dehydrogenation of normal paraffin to monoolefins, this catalyst life is only 90 days. So after 90 days, this is platinum based. We have to put the new catalyst. So if I can do some ALD on it and extend the life to even 180 days, it will be a big change. Because changing the catalyst also is costly. So all supported catalysts where we use costly or noble metals as a active component, that is a very good, I think those are all good candidates for ALD. And ALD practicing on a large scale, at least we believe it is not very difficult.
So the ALD is used not for the active component. I mean, is it to increase the life of the metal catalyst? I mean,
yes, ALD will be like, see, atomic layer deposition. You put some small layer, which is like maybe 40, 30,
for
40.
every material, you need a proper source. For ALD, the source material is may not be.
What we can do, I'll tell you. See, I use alumina as my catalyst support. So alumina on which I put, let's say, platinum or palladium. Then alumina has got hydroxyl groups always. So I can use this hydroxyl group and use this aluminum alkoxides. They can be reacted with only OH groups under some controlled condition. So then this alumina gets deposited one layer. I can just one monolayer of that. Then that alkoxide will again can be hydrolyzed to create hydroxyl group on which another layer of alumina can be put. Like that I can decide how many layers I want to put depending upon the desired thickness. So this is possible. We have done in the lab on not maybe 100 gram per 100.
Cluster beam deposition, and I mean there are some techniques which are I mean developed in UK and I think basically in Europe for these ultra small cluster deposition.
So that is also very important. That is also cluster metal cluster is very important. And also I have few example I didn't show where the if you control cluster of metals also enhances the selectivity very high.
Through physical deposition I'm talking about.
Yeah,
okay.
Yeah.
Okay, you have used those.
No, I have not used this cluster thing, but I have read a lot of work done by this Royal Institute.
Yes. Yeah.
Professor Thomas has done a lot of work on it.
Yeah. Okay, thank you very much.
Now I would like to request Dr. Nageshwar Rao Pilla to ask his question. Could you please unmute yourself, sir?
Okay, thank you. Okay, sir, thank you very much for your talk. Excellent talk. So I have like similar question on this ALD.
Yeah.
So like when you have supported catalyst, like the supported catalyst, the nanoparticles are inside the pores.
Yeah.
Now, like how do we have this ALD on these like onto these like nano clusters when we have these nano clusters inside the pores? Like I mean, like still can we get the like uniform layer onto these clusters even though these are inside the pores?
Yeah. See, as I told you, basically when you use a support is very important. We have to, any support, normally alumina, let's say alumina we use or silica we use, they all have hydroxyl groups on it. So we have to have some hydroxyl group created on this alumina as our support, which already has got this metal deposition done on it. Now these hydroxyl groups, then we have to react with like something like triethyl aluminum. You know, these alkoxy aluminum, they are very reactive. The moment they see OH group, they will immediately get hydrolyzed. and then you keep the concentration such a way it's only forming a monolayer on the alumina surface. You can even calculate the surface density of hydroxyl group, and accordingly you can put this teal amount on it. So once monolayer is formed, all hydroxyl group is consumed, then on that monolayer you can again introduce some amount of moisture. That will further whatever left RO group will get hydrolyzed, and then will create on that monolayer again OH groups. So then you can put another monolayer of your teal on that. Like that you can do it 30 times, 40 times and create certain 40 layers of monolayers of alumina, and then you can get the desired thickness of the layer on this thing. So the most of the people, if you have got titanium support, then also you can do silica, you can use ceria, because all these oxides you can always will have hydroxyl groups which we can use for reacting with this very reactive teal type materials.
Okay, I got you. Basically, my question was basically like, for example, in your reforming reaction catalyst, you have this platinum and tin, and let's say this platinum and tin are inside the pores of a support.
Yes.
So in that, like in that case, will you still get the oxide layer onto these platinum or tin clusters when you do the ALD? That is my question.
Yeah, see, it will, because whether you are in the micropore or nanopore or mesopore, basically I don't see, I see it as a surface. No? So the surface area is available to me. There will be hydroxyl group even inside the pores, na? And my teal will go inside the pores. So these are small molecules, they will react there also.
Okay, okay, I got you. So now I have one last question. Basically, like you said that you avoided the chlorine, like by that way, like I mean chlorine, let's say tin chloride is acid catalyst that you are using, but you avoided chlorine by making oxide layer. So this oxide layer, like let's say this tin oxide, will it act as a acid now, acid catalyst now? Because you eliminated the tin chloride, so your acid catalyst is now gone. So now what is your acid catalyst now in the new catalyst?
See, this in forming catalyst, tin and platinum, they don't act as any acid. They are metals. They are reduced. They are reduced. They only are used as metals. PT0 and tin 0. So the acidity is not coming because of acidity comes because of your alumina, and they chloride alumina to get some requisite amount of acidity for doing this dehydrocyclization and other reactions. If paraffin to they are little difficult, whereas cyclic compounds can be converted to aromatic easily, but for those you need more acidity. That's why they put chloride on alumina. If I can get that acidity without by putting chloride, by putting some nano sheet of some other oxide, which gives me acidity as well as covers my platinum and alumina, that is the innovation we could do.
Okay, 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 got you. Okay, excellent. Thank you very much, sir. Yeah.
Thank you so much, sir, for presenting such an informative talk and addressing to the question and answers. And with this, we have come to an end of the day one schedule. And I would like to request all the participants to join us tomorrow at 9 a.m. for the day two schedule. We are having lab sessions, which includes the Center for Nanotechnology facilities. And we have some talk by Dr. Divyendu Das and Dr. Swapnil Sinha as well. Thank you so much.
Thank you.